Hello class, this is Mrs. Ayodeji with today's video on 11.1 power functions. As you're watching the video, please feel free to write down any important vocabulary, formula, equations. Don't forget you have the option of pausing, rewinding, and repeating as often as you need the video if you don't understand something. And with the conclusion of watching the video, write a brief summary about what occurred in the video and submit that summary as well as any deep and thought-provoking questions that you had about the video or about the concept in the video. Okay, let's begin. Today we're going to start talking about power functions, but before we can talk about power functions, we have to talk about proportionality. And both of these concepts you've actually used before without using the word proportionality or power functions. So there's two types of proportionalities. There's directly proportional and inversely proportional. And these are the definitions of each of these. And these should look very familiar to you. But I want you to get the notation and how we say it correctly. So in this case, because of this equation, we say that y is directly proportional to a power of x. So, and the reason why we say that is that I can get y value by basically taking a power of x and multiplying it by a constant. Okay? We say that y is inversely proportional to a power of x if y is equal to k divided by that power of x. Okay, so in this case k and n are constants. And so of course the next question is, when will we see this in real life? See, I've already anticipated your questions, and those are very popular questions. So where we've seen direct and inverse proportionality is in popular formulas. If you recall, the simple area formula for the area of a square is an example of directly proportional. So we would say the area of a square is directly proportional to the side length of the square. Okay, actually let me correct that. The area of the square is directly proportional to a square of the side length. Okay, now these are also examples of directly proportional, but they include multiple variables, not just a variable and a constant. So if we keep the b constant, we can say that a is directly proportional to the height. 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 Because if b is constant, then b becomes a constant. 1/2 b becomes a constant in b. Now we could also say that h is constant, and we would say the same thing, that a is directly proportional to the base, a is directly proportional to the base, and a is directly proportional to the base. And here we have a physics formula chart where there's a lot of multiple variables in the same formula, but there's an examples of directly proportional, and I've highlighted all of these. Now, indirectly proportional, there's not that many examples here in the physics, but here's an example of indirectly proportional. So we would say that T is indirectly proportional to whatever this W represents, and this is a omega in Greek letters. So T is inversely proportional to omega. Now, as you notice, we have yellows and we have a few blues, but we also have some greens. Well, greens is because there are multiple variables, and some variables are directly proportional to the function and some are not. So for this example, acceleration, I don't know what this A represents. Okay, let's do F. Force is equal to mass times, no, I don't want to use that either. I know you guys aren't familiar, so we'll take a look at this example. This F is directly proportional to Q1 or Q2, okay? But it's inversely proportional, I think that's to T, to a square of T, okay? So this can be both directly proportional and inversely proportional or indirectly proportional, but you use inversely proportional, okay? So how does that relate to the topic power functions? Well, all power functions are basically examples of directly proportional relationships. So F is directly proportional to a power of X. And that, in this case, this is an example of a power function. So let's take a look at what happens to the power functions if I modify the power P. Okay? So let K, the constant of proportionality, or the constant, be considered 1. So we're just dealing with y equals x to the P. So what happens when P is 0 and what happens when P is 1? Well, you guys should know what these graphs are without even me graphing it, but y equals x to the 0 means y equals 1, so it's a horizontal graph. at y equals 1, and y equals x to the 1 is a linear graph, a slanted linear graph, and of course it goes through the origin. So these are very simple cases when p is a 0 or 1. But what happens when p is not 0, 1, but it's still a positive integer? Well, you're going to have to end up looking at two cases, when p is odd and when p is even. And we're going to use Desmos to demonstrate that. So here we have y equals a times x to the p, where a is 1 and p is a power. And let's see what happens when p is an odd integer power. So I'm going to press play. And as you can see, this is what the shape of the graph looks like. No matter what power p is, as long as it's the odd integer power. Okay, and it seems like as p increases, this chair-looking thing is looking very much slimmer and slimmer and slimmer as p increases. Okay, now what if that's when p is odd? What if p is even? Oops. So let me change this p to an even number, and let's increase it. Looks like a parabola that's getting skinnier and skinnier, or more narrow and more narrow. So all p's that are positive integers that are even looks like a type of parabola, and all p's that are positive and odd looks like a chair. And so going back to our notes, we can say that when p is an odd number, the graph is symmetric about the origin and the range is all real numbers. And when p is an even integer, it's symmetric about the y-axis and the range is not all real numbers. Okay, and this is an example. So now the next question might be, what happens if p is not a positive integer, but what if it's a negative integer? Okay, and in order to represent p as a negative integer, we can break it up into odd negative integers and even negative integers too. But to understand what the graph looks like, let's rewrite these negative integers in a version that we're used to. So y equals x to the negative 1 is the same thing as 1 over x, and y equals x to the negative 2 is the same thing as 1 over x squared. So you can see as x gets bigger, the denominator gets bigger, and therefore the function values get smaller. Okay? So that's essentially what's happening in this sense. So let's take a look at a graph of this using when p is a negative integer. Okay. So to keep that, let's take a look at the odd negative integers first and see what they look like, what the graphs of those look like. Oops, gotta put them on. So this is when p is a negative even integer. Negative even integer. This is what the graph of the power function looks like. And it seems like the range is always above the x-axis, above the x-axis, and it seems to have a vertical asymptote there on the y-axis as well as the x-axis, since it never goes below it. That's when p is a negative even integer. What happens when p is a negative odd integer? Let's see what happens there. So now we have a slightly different graph. It still is separated by branches, but one branch is in the first quadrant and one branch is in the third quadrant. And this is what happens when p is a negative odd integer. Okay, so as x, for both of those situations, as x approaches infinity, from both the positive side and negative side, we end up with function values being closer to 0, which makes sense, which means we have a horizontal asymptote at y equals 0, or the x-axis, regardless if p is positive, a negative even integer or a negative odd integer. And as x approaches 0, the power function values seem to get closer to infinity, which implies that there's a vertical asymptote. So whether p is an odd or an even negative integer, you will always have a horizontal asymptote and a vertical asymptote. When p is an even integer, the range is only positive numbers, and when P is an even negative odd one number, the range is all real numbers except 0. Okay? All right, I know what I said may be confusing, but take a look at the pictures again to get a good idea. All right, so we've talked about what happens when P is positive or negative integers. What happens when P is a fraction? And we're not going to do all fractions, but just take a look at these fractional powers. So it seems like it's 1 over an integer, positive integer. And we're going to have different graphs too very quickly using Desmos. When P is a positive fraction, let's look at what happens. This is when P is a 1 over an odd number. It looks very much like the chair, but rotated. And let's see when P is 1 over P, where P is an even number. It looks like part of a parabola, half of the parabola. Okay? So you're either going to have a graph that looks like this or a graph that looks like that. And in this case, if P is an even integer, the domain and range are both restricted to only positive numbers, including 0 for the domain, but not including 0 for the range. And when P is an even number, the domain and range are all real numbers, and they look like part of a square. Okay? The last thing is how to find the formula of a power function. And the thing is, you need to know what K is and what the power is. The constant proportionality is the K. Oops, I had to fix that. So when we're finding the formula for a power function, if you remember from the very first page, power functions look like this. We need to figure out what K is and what the P is. What the constant of proportionality is, that's K, and what the P is, the power is. And unfortunately, you can't easily do that for all powers of P, but for some powers of P, you can easily do that. And that's for linear and exponential functions. You can find these using 2 points on a graph. So here's an example, and you can read it. Teachers are loud over here. And we're going to take the 2 values, a D and a V value, and another D and a V value, and use it to determine V as a function of D by determining the constant of proportionality. So we need to figure out what K is, and then we need to figure out what P is. Okay, you can only do one of those at a time. So we're going to take the first set of numbers, the first pair, VD pair, and then we're going to compare with the second DV pair to figure out what K is. And so we do this, V over V, okay, V over V, and then what D is based off the relationship because it's directly proportional to a power. Oops. Wrong one. Sorry, wrong color. This should be yellow over green. Okay, and that's how we end up with this. And so we're able to determine actually P, not K, from this. So P must be equal to 1/2. And once we have P, then we can plug it in to figure out what K is. All right, if this is confusing, you can come talk to me or ask the question, but I've got to end the video. It's way too long. Have a good day.